All right, this is our final lecture on polynomials before we move into rational functions. And so in the last lecture, we talked about how to find real zeros of polynomial functions. Today we're going to talk about complex zeros and the fundamental theorem of algebra and how to write a polynomial given a list of its zeros. Okay, so before we get to any examples, I just want to make sure that we're all clear on all of the vocabulary that we've talked about in regards to polynomials, and I'm going to introduce some new things here in section 2.5. So let's make sure that we're clear on a couple of things. First, the fundamental theorem of algebra, very important theorem that says if a polynomial function is of degree n, it has exactly n complex zeros. Now what that means is that some of the zeros might be real, some of them might be imaginary, and some of them might be repeated, meaning they have a multiplicity that's bigger than 2. But all together, they have to add up. The number of zeros has to add up to whatever the degree of the polynomial is. In section 2.3, we talked about multiplicity. That was a number of times a zero or a factor repeated. And then something new here in section 2.5 is if x equals a plus bi is an imaginary zero of a polynomial, then its conjugate, a minus bi, must also be a zero. So for example, if I tell you that 3 plus 2i is a zero of a polynomial, that means that 3 minus 2i must also be a zero. So these imaginary zeros have to come in pairs. Real zeros don't have to do that. If 2 is a zero, negative 2 does not have to be a zero. But imaginary zeros have to come in pairs, and they always come in conjugate pairs. Okay, in section 2.4, we talked about the factor theorem, which essentially said, just for example, if I say that x is equal to negative 2 is a zero, then that means that x plus 2 is a factor of the polynomial. Or if I say x is equal to 7 is a zero, then that means that x minus 7 has to be one of the factors of the polynomial. And then finally, the last new thing is this nice little theorem that basically says every polynomial function that has real coefficients, and we're not going to talk about any other type of polynomial function. Every polynomial function we talk about is going to have real coefficients, but it might have imaginary solutions or zeros. So make sure you understand the difference between when I say real coefficients, meaning the numbers in front of all of the terms, versus solutions or zeros, meaning the answers of the polynomial, if you want to think about it like that. So every polynomial function with real coefficients can be written as the product of linear factors. So what's an example of a linear factor? That would be like x plus 2 or x minus 7, and an irreducible quadratic factor with real coefficients. Now, what is an irreducible quadratic factor? It is a quadratic that has no real solutions, meaning both of its zeros are imaginary. And so we're going to see at the end of this lesson that every polynomial can be written as the product of linear factors like x plus 2 or x minus 7 or x plus 5, and irreducible quadratic factors, for example, x squared plus 6x plus 10, which does not have any real solutions. So we'll get there. That's where we're headed by the end of these notes.